smaller. So the overhead, in fact, didn't matter to 2 digits. So that's good. You'd like the overhead to be negligible. In this case it is. So we really didn't even need to worry about the overhead.
So
Yeah.
does that mean that does that mean that the entire time spent on the function is simply just the for loop? Not even the binary search?
No, no. It's saying this is the time for the for loop plus the binary searches. This is the time just for the for loop.
Okay.
But this is a couple orders of magnitude smaller than that. So the binary search dominates the time. The for loop overhead is literally negligible because if you only care about 2 digits, it has no effect at all. Yeah?
I was going to say, if we're really worried about it optimizing things, you could just add the updating the loop variable into the actual loop rather than condition, right? And that wouldn't optimize it.
Okay, update loop variable where?
Within the loop instead of in the actual condition.
Well, it would still be, I'm timing the loop, I'm timing the whole loop from beginning to end. So anything that happens between the beginning and the stopwatch is going to be measured.
Yeah. So I'm saying when you're calculating your overhead, if you added even just a meaningless computation, but you added it to both of them, then that should still work, right? Like
I'm not catching on. Maybe I can talk to you later about that. You had a question, yeah?
Why was the time when we stopped the stopwatch and then started off getting inside the loop bigger than the time when we measured the whole loop?
It's not. This is the whole loop, including binary search. This is the same thing, except the binary search is commented out.
I'm talking about like number 2.
Oh, why did I get .00038, and then the next time I get .00032?
The second time we got .004 or something, and then the third time we got .000.
Okay, the second time we kept turning our stopwatch on and off.
It's going to take longer than measuring the whole loop.
What I'm telling you is that it's not, you shouldn't use these timers to time small intervals, like individual binary searches. You should have them measure big things, like entire loops. Just like the nurse doesn't take your pulse 1 beat at a time. The nurse measures your pulse for 15 seconds and computes an average. Yeah?
So as a timing strategy, whatever we're timing, if we have a lot of overhead in it, we can always just time again with like the overhead average.
Right.
But you want to try to reduce the amount of overhead in the original.
Yeah, make the overhead as small as you can. Then, you can still subtract it out, but hopefully it'll be negligible and won't matter. Okay, how can we improve this? Are we really following my advice of only measure long intervals of time? No. How long does it take 1,000 binary searches? Certainly not a second.
0.32 seconds?
Yeah, we could take that number and multiply it by 1,000 and measure it. Yeah.
Not very long.
Not very long. So my goal is 0.32 milliseconds. These answers are in milliseconds.
Yeah.
I want to time a second's worth of these binary searches. How many times will a loop have to run to accomplish that? I also don't want to spend a lot of time figuring out how many iterations to do. So you can think of a way to make the loop run for a second without figuring it out in advance. Yeah?
Change the for loop to a while loop and then have the timer stop the loop after 1 second.
Well, okay, that's one idea. We could let it run, and we sort of keep looking at the watch and then stop the watch when it got to a second. But I have another idea that actually has an additional advantage. Yeah?
Run it like an absurd amount of times, like 1 million times or something.
Okay, I could run it an absurd amount of time, but the problem is that might work for binary search, but if I then start measuring selection sort, 1 million is going to be way too big, and the loop's going to run for minutes maybe. So here's my idea. I'll just pick some number like 2. I will run 2 binary searches. I'll let my loop run twice. Do 2 binary searches and time it. And if that took a second, good. I'm done. If it didn't take a second, I will double that 2 to 4. I will run the loop 4 times, time that. Then I'll run it 8 times, time that. 16 times, time that. Eventually, I'll get to a number big enough that the loop it'll take a second for the loop to do all the binary searches. Now, how long will it take? Let's say I start with 2 iterations, then 4, then 8, then 16, and stop when I hit a number of iterations. It takes a second.
It's like 2 seconds.
That would take 2 seconds of time, right? So it would take 1 second figuring out the right number of iterations, and then another second to do that number of iterations. Okay? The reason being that if you add like 1 plus a half plus a quarter plus an 8 plus a 16 plus a 32nd, you get 2. But that's not my main point. What's the advantage of sneaking up on it like this instead of saying, just calculating the right number of iterations to do it?
You have your second of warm-up time.
What's that?
You have your second of warm-up time.
We have my second of warm-up time, exactly. So while I run it twice, then 4 times, then 8 times, then 16 times, and 32 times. All these times, I'm not using the measurements except to figure out how many times to ultimately do. All those preliminary runs take a second. So I run my program, end up running my algorithm for a second before I take the measurement that matters. So I get my warm-up. Let me show you what the code looks like when I do that. So if you look right here, you can't really see that. You look right here, that's the loop that I had before. I do it for some number of repetitions, I do the binary search, and I time the entire loop. I just put that inside of the do loop. Each time I go to the do loop, I double the number of repetitions from the previous time. And I keep doubling the number of repetitions until the elapsed time hits a second. And when it hits a second, I'm done. I compute the average that last run took. Yeah?
Never mind. I was about to ask why you restart instead of start, but I understand. You're adding it up.
Okay? So I just time for some repetitions. If that wasn't long enough, I time it for twice that many repetitions. If that wasn't long enough, I time it again for twice that many. Eventually, I'll measure it, and then it'll take a second, and I'll accept that measurement. And I will have used up a second of testing time previously to warm everything up. Yeah?
Is there a heavy difference between using a do or a while loop?
No. You ask if there's a heavy difference in using the do and while loop. It just worked for me here. I probably use 1 do loop for every 100 while loops I write. But in this case, I needed to do the test at the end because that's when I had the elapsed time. So I do that. And how do I count for overhead? So I'm measuring this loop which contains the overhead. How do I get rid of the overhead? Same way. I just do the same trick on the loop without the call it binary search. Now, yeah?
But now you're taking out the binary search, so by the time you reach the duration, would you have the same
No. Because, okay, so the thing you realize is, well, the number of repetitions it takes to reach a second on this code be the same as the number of repetitions it takes to get to 1 second on the original code that calls binary search. No. It will take a lot more repetitions for this code to take a second than if I uncomment this. So, but what I do is I compute an average per iteration. So I'll have elapsed time divided by a much larger repetitions count for the overhead than I will for the other. So I just compute the 2 averages and subtract them. And that gives me the measurement. So that takes care of everything I wanted to do. So let's see how that works. I got the warm up. It's time to generate the jitters. The just-in-time compiler has time to run. So this ought to take about 2 seconds. And that's quite a bit smaller. What we were getting like 0.0003 something, 32. Why did it get so? Why is it smaller? What are the things that we're controlling for now we weren't before? Yeah.
So with averages are heavily skewed by outliers, and if you have like your warm-up, that takes like 0.1 milliseconds, while everything else takes that amount of milliseconds, it'll skew the average. So if you take it for the whole second, then you're pulling everything down significantly more to the actual
Okay.
value.
So before we were timing a loop of length 1,000. Some, or if not most of those calls to binary search, we were still paying a large amount of overhead in terms of populating the cache and compiling the code and all that. This way, by letting it run for a second before we start the timing, that's all taken care of before we take the final measurement. And so the average is 3 times lower in this case. And again, the overhead is negative. Okay, now my stopwatch measures clock time, wall time, elapsed time, real time. Why is that sort of the wrong thing to use? Measuring a computer program, yeah.
Because your CPU doesn't follow the wall time.
Right, I may not have access to the CPU the whole time, right? A program can run and get swapped out and be idle for a while another process runs, and then get swapped back in. So there's a different timer in C#, process timer. And that's what I do in this one here, time binary search 6. So the only difference is, no, this is different. Oh, sorry. Okay, hold that thought. This one measures, before it was measuring, version 5 was measuring the amount of time required to find the last element. This determines the amount of time required to find an arbitrary element. So the average amount of time for a lookup. And so the difference is, instead of doing a single binary search, each time I look up each element in the array. So in the old measurement, all I had here was this call. I didn't have this stuff. This version now, I'm actually doing 1,024 lookups each time, so I'm computing the average for an arbitrary lookup. I'm just got to be sure to measure by the time, divide the time by the number of repetitions and the size of the array to get the average. So would you expect the result to be bigger or smaller? Smaller, because we were measuring the worst case before. Is that smaller? I don't remember. Yeah, well, it's like I say, it's an inexact science. I always got that veil. So it was 1/8 in there. Perfect.
Just do it again.
Yeah. Okay, so then number 7 actually uses a process timer, processor timer. So in theory, it's just the clock is only running when your process is running. So that is number 7. See if that makes any difference. About the same. And then the last few things I want to show you are get to the doubling behavior. So let's do test A, which is average time for binary search for the last element for various sizes of array. So for size 63, that's the time. And that delta column you're going to see is a difference between this time and that time. Okay, so what we're expecting to see is it goes up by the same amount each time we double. Now it's never exact, but it's sort of hanging out in the same area, at least in the same order of magnitude. And each of these timings is being derived by the process I just showed you. It keeps doubling the number of repetitions until it finds one that works. Okay, so that's what a logarithmic algorithm looks like. Okay, and let's see, number 9 is the average running time, which is still going to be logarithmic. Number 10 is a linear search instead of a binary search. Now, what we're going to expect to see here? I'm going to show you the ratio between successive timers. So I'm doubling the size of the array each time. What's the ratio going to be? We expect to see a ratio of 2. So a linear algorithm ought to show a ratio of 2. And what often happens is when you got small numbers, it doesn't quite work out because it's not, there's some low order terms. But typically, what we like to see is it heads toward 2 and pretty much stays there. Although it's never perfect, often you get to a really large array and suddenly there's a discontinuity, and I can blame that on the array doesn't fit in the cache anymore or something. I can always make some explanation of it. Yeah.
Just out of curiosity, could this experiment be improved by doing 50% successful searches and 50% unsuccessful?
Well, it depends what you're measuring.
Okay.
So here I'm trying to measure successful lookups. Yeah, you just have to decide what you're measuring and devise an experiment to do it. So you can see it's settled down to pretty close to 2. And that's good evidence that we're dealing with a linear algorithm. Any last questions about this? Yeah?
Probably a stupid question, but with this search, we're searching and sorting through numbers, correct?
Mm-hmm.
Would it be more time when you have numbers that are larger than, let's say, like 3 digits and so on?
No, okay, so he's asking about what the size of the size of the numbers matter, and the answer is no, because the integer arithmetic is done in the machine, and it doesn't really care how big they are. Now, if what we had were big integer objects that could be, many, many bytes long, yes, the size of the digits would matter, but the numbers would matter. Yeah.
Which of these strategies do you recommend we use for our assignment?
Which strategy? Strategy like the most evolved one, which is like versions 4 and 5. I'm sorry, 5 and 6. 5, 6, and 7. Yeah?
Did you arbitrarily choose to start at size 63, or was there a specific reason that we didn't start at really low numbers?
For really low numbers, I don't know why I picked 63, but for really low numbers, you typically just get noise. Okay? Yeah, this is working pretty well. Better than it usually does. All right, let's take a break and we'll talk about a different aspect of complexity.
I know, I'm asking if he's going to be at
So are you generally free for this class? I'd like to talk to you in person. Ready to go? All right, let's get started again. Okay, so now we just talked about experimental complexity, measuring things experimentally. But you know, you can spend a lot of time trying to measure things experimentally if what your goal is to figure out the doubling behavior, or in other words, the asymptotic complexity of an algorithm. A lot of times it's easier just to do it analytically, to think about it, look at the code. So I want to talk about that, and along the way talk about notation we use for that. So what you're looking at here is a scatter plot. I'm going to animate a sorting algorithm. And the way to think about this plot is, think of this as being an array of elements. So the size of this array is 64, I think. So think of this as being indexed from 0 to 63. So you'll notice that there's one square in each column, from left to right. And then on this dimension, think of this, the square tells you the magnitude of the number, the number that's in the column. So this column contains 0. So this is 0, up the top is 63. So here's 0, here's 1, here's 2, here's 3, and so on. And the largest number is up there in that column. So if I were to sort this into ascending order, what would the picture look like? Right, I'd have a straight line, so I can do that. I can just go here and order it in ascending order. So a sorting algorithm is going to rearrange the randomly permuted space into something that looks like that. Or if I sort it into descending order, you'd expect it to end up looking like that. Okay? But I'm going to permute it, and we're going to run the algorithm and watch the array rearrange itself, get rearranged by the algorithm. Okay? So I'm going to animate selection sort. So here's the algorithm, selection sort. And before I click start, also I want to note you I've slowed it down, so I'm running it at a slower speed than full speed. How does selection sort work? Who could remind us how selection sort works? Yeah?
It'll iterate through the whole process to find the first piece.
Okay, it'll go through the entire array to find the smallest element. It'll find that, and what will it do with this element?
Immediately put it in its place.
It'll swap it with whatever's in this column. So it'll take, no, that's the biggest element. I was wrong. No, this is a different permutation. So it'll take the biggest element, it'll take that element, which is the one that happens to be in this column, and just swap it. So what will you see? So each time it's going to go through it won't touch this column anymore. Next time it'll go through the remaining columns, find the smallest, and swap it to that column. What's the picture going to look like? Yeah? You'll see the diagonal line grow, and at the end it'll fill the screen. What will it look like halfway through? Half a diagonal line, half scatter plot. Yeah, it's very characteristic. So let's watch this. So the red flashes you're seeing are, every time it compares two elements, it flashes in red. And those little lines are being left behind are an artifact of my display. I can't seem to figure out. It's the bug in Java, I think. Okay? So you saw it rearrange itself. Now I'll put this at fast speed, and I'll go to, say, 256. You sort of see the same deal. Now, unfortunately, the artifacts are even more distracting here. Okay, so that's selection sort. Now, we're also going to look at insertion sort. So I might as well do that now. So let me go back to size 64, slow speed, permuted. What's insertion sort do? Yeah?
If I remember right, there's an empty array that's sorted, and then there's a full array of unsorted, and it just puts one into the sorted with a 10.
Okay, I think you got the right idea. You're sort of describing what it'll look like. Yeah?
It takes whatever the first element it finds, it takes that and it puts it in the correct place in the sorted list.
So what it does, leaves the first column alone, it doesn't look at it initially. Then it goes to the second column, it moves this element as far to the left as it can. It moves it to its proper place in the already sorted elements. And it keeps repeating that process. So it's a little harder to describe than a selection sort, but it's easy to see what's going on when you're running. So here we go. That ain't insertion sort. So why are you seeing this ripple effect? Because each new element, it compares it all the way down here. It just basically compares and moves it all the way down to its correct spot. So this one will cause a fairly long ripple when it gets put in. And you end up sorted. So how would you describe its look when it's half done?
Smushed.
Squiggly lines. It's in reverse.
Okay? So at any given time, the left portion of the array is sorted, but it's not in its necessarily its final look, right? Because they're still thinking, with selection sort, you had a perfect sort of some elements and then a scatter plot. Here you've got still a sort. It's not everything's not necessarily in its final position, and then you got things yet to be inserted. Yeah?
And because of that, like in the selection sort, it was only the top corner that was unsorted. Here, the entire right half is
Right.
unsorted.
So it's been years since I've done this, but I've actually put questions like this on exams. I'll take a screenshot of one of these algorithms and say which one is it. It's very characteristic. You cannot mistake this for any other sorting algorithm when you look at it. So let's try this. Let's start with a sorted array. What's going to happen?
Still have to check to make sure everything's,
Okay? It's very fast because each time it finds the next element and tries to push it to where it belongs, it's already where it belongs. So it's just basically verifying it's sorted. So insertion sort's really fast when the array's already sorted. If it's reverse sorted, though, it's particularly bad. So it looks like that.
This is getting really weird.
Well, it's sort of erasing my artifacts as it goes by. If I set my screen to full resolution, it doesn't happen. It's just when it's on this. To record the class, I have to use a lower resolution, and it just screws up for some reason. Okay, now the last thing I want to do before I move on, stop that. Let's go to 256. Let's set the speed to fast. Let us permute, and let us run selection sort. So you can get a feel for how long selection sort takes. Okay? Then let's go to insertion sort. Okay? Does that seem faster? Yeah, it turns out insertion sort is going to be about twice as fast on average. This is all skewed, of course, by the graphics operation I'm doing. It really slows it down compared to just sorting an array. But then let's look at quick sort. Okay? Algorithms matter. Okay, let us assume that we want to find an upper bound on the running time of selection sort. In other words, the running time of the worst case. So there's our algorithm. How do we do it? Yeah.
I just had a question about,
Yeah.
is there a way to download that software?
I can post it on the webpage if you want to. And then you can solve my artifact problems, let me know. Okay? Let me propose one way of doing it. There's the code. What we could do is just painstakingly go into the code and say, okay, there's this, it does that, it does this. These are all the things that it does at some point. And then we could count. We could carefully count. Assuming there are n elements in the array, we could count how many of each kind of operation it does. So let's try that. How many times does it do int I equals 0? Once. How many times does it do I less than data.length? Actually n plus 1. N times it succeeds and 1 time it fails. I plus plus, n it turns out, not n plus 1. N at smallest equals I. How many times does the loop run?
N times.
N times. So it's going to do that inner loop initialization n times. J less than data.length. Now where does that come from? So this loop itself runs n times because, n different times because it's inside the outer loop. The number of times the inner loop runs depends on how big the starting point is. So the first time the inner loop runs, it's going to run longer. The last time it's just going to run once. So it's the sum of those things. How about the J++? Again, it depends. The first time it's going to do, okay, when I is equal to 0, then we're going to end up doing J++ n minus 1 times. But when J finally gets up to data.length minus, when I gets up to data.length minus 1, we're not going to do it at all. Because the condition, J less than data.length will fail right away. Okay? Same token, we could do that count, we could do that count. And we swap, when we swap n times. Okay, so we've done this careful count. And you'll notice that it can be tough to count what's going on inside of a loop. Of a loop inside another loop. Because the starting point changes each time this loop runs, and so that controls the number of iterations. That's why all these sums show up. Okay, so we want to figure out the running time of selection sort. So what do we do next?
Add them together.
Okay, well, can we just add all these operations together and say, okay, it takes this many operations, therefore this is its running time? I mean, I'll be really concrete. I want to predict how many milliseconds it'll take, how many microseconds it'll take the program to run as a function of n. So what I'm going to have to do? Yeah?
You need to have the time per operation.
Okay, I'm going to need to figure out how long it takes to execute this. How long does it take to execute this? How long, I want to compute the time. And then I might discover, well, it does, it's more complicated. Maybe we should look at the bytecode and count operations in the bytecode. Anyway, but before we do that, before we measure the time of all the operations,